Hello students and welcome to this calculus lesson. In this video, we're going to be looking at another problem concerning related rates. So let's get started. All right, and I'm going to tackle these problems in a very similar manner. As I read this, I'm going to just outline what's important here. So a stone is dropped into a calm body of water. And as that stone hits the water, we've got some circles that are going to expand from it. So we've got this concentric circle stuff happening, all right? The radius of the outer ripple is increasing. So the radius of the outer ripple is increasing at a rate. It's a rate. So what's the rate of? It's the rate of the radius. So this is going to be dr dt. So when the radius is exactly 4 feet, so this is going to be our radius, at what rate is the total area of the disturbed water changing? So rate, total area, so we're looking at dA dt. That's what we want to find, all right? So identify everything that we have in here. Well, we've got the radius and we have the area, all right? So now we want to say, okay, what's going to remain constant? Well, in this case, again, no variables remain constant. Don't worry if you're not sure exactly what it means to remain constant yet, because we are going to be looking at some problems where there are going to be variables that do remain constant, okay? Now we want to say what's given and what we want to find. All right, so what's given in this problem? Well, we know that the rate of the radius is changing with respect to time, and that is given as 1 foot per second. That looks like a nice number, but what we want to find is the rate that the area is changing with respect to time. So what is going to relate related rates? What is going to relate everything between radius and area of a circle? Well, that's going to be equal to A equals pi r squared. Nothing really to substitute yet, but we will if we need to. So taking that function a equals pi r squared, we want to actually take that derivative. So again, without looking at my notes, I'm just implicitly differentiating here. So here I've got dA dt, because it's with respect to time, equals pi r squared. So the 2 is going to go down, so it's going to be 2 pi times the radius, subtract 1 from the exponent, and we've got our breadcrumb dr dt, okay? So now it all comes down to substituting right here in for those variables where we don't know dA dt, okay? We don't know that, but we do know 2 pi, and then the radius is 4 feet. Again, putting those units in there, and now I have 1 foot per second when it comes down to the rate at which the radius is changing, okay? So now I just want to figure out, okay, what is dA dt here? So dA dt equals, okay, so 2 pi times 4, that's going to get me 8 pi. Now, notice here I've got foot in my numerator and foot in my numerator. So that's going to get me square feet, okay? And then seconds remains in my denominator, okay? And then I also multiplied by the 1 there. Again, it doesn't really change anything. So we know the rate at which this area is expanding at a rate of 8 pi square feet per second. Okay, so that's actually growing pretty quick, all right? And if you think about it, the area as something of that circle should get a lot larger quickly as it starts to expand out, okay? And this is going to be example number 2. You have a lot more tough examples coming up. We're going to keep scaffolding. We're going to keep going up. We're going to keep getting tougher, but start practicing these problems on your own. Look at other free response questions. Look at your homework. Attempt those problems as we go, and take a pause for each of these and try to just see if you can go about it the exact same way. Of course, if you don't understand anything here and you need help, please reach out to me. I'm Mr. Hernandez, and this was Mr. Hernandez Teaches.